So here we have the 2014, this is question 2, leaving cert ordinary level, and there's a question on complex numbers. So we're told z1 is equal to 5 minus I, and z2 is 4 plus 3I, and I squared is minus 1. First we're asked to find z1 minus z2. So z1 minus z2, so it'll be z1, which is 5 minus I, and then minus the whole of z2, so I'm just going to put it in a bracket, 4 plus 3I. So the 5 minus I, there's no minus in front of that, so that'll still be as it is, but then the minus will go to the 4, and it will go to the 3I, so it'll be minus 4 minus 3I. And now I'm going to group together. I can add together my real parts and I can add my imaginary parts. The real parts are the parts that don't have an I. The imaginary parts, say in this is the real, this is the imaginary, and this is the real, and this is the imaginary. So I'm going to underline the real because I can put them together. So this is real and that's real. So 5 take 4 is 1, and then this is imaginary and this is imaginary, so minus I. So minus I is the same as minus 1I. So if I put them together, I'll get minus 4I. So z1 minus z2 is 1 minus 4I. And then I'm asked to verify that z1, the absolute value, so that means the modulus of z1 minus z2 is equal to the absolute value of z2 minus z1. So firstly, I'm already after getting z1 minus z2, which is this. So I have to do what's inside the modulus lines first, and then I get the modulus of that. So z1 minus z2 is 1 minus 4I. So the modulus means the distance from the origin. So say, I'll just go through it quickly. So say if I had a complex number and it was a plus bi. So it went across a and up b. Say we'll call this distance from the origin or. So if I wanted to get that distance or, I could use Pythagoras, and it could be or squared is equal to a squared plus b squared. But if I didn't want or squared, I just wanted or, the modulus, it'd be the square root of a squared plus b squared. So if I have a complex number a plus bi, the modulus of that is equal to a squared plus the square root of a squared plus b squared. So the modulus of this, the modulus of z1 minus z2 is going to be equal to the square root of 1 squared plus minus 4 squared. So the 1 squared is just going to be 1, minus 4 squared will give us 16, so the modulus of that will be the square root of 17. But now we're asked to get the modulus of z2 minus z1. Well, first I'm actually going to have to get, I'm going to have to do what's inside my modulus lines first. So I have to get z2 minus z1. So z2 is 4 plus 3I. And z1 is 5 minus I. So z2 minus z1 will be 4 plus 3I minus all of 5 minus I. So that minus will go to the 5 and it will go to the minus I. So 4 plus 3I, and then that'll be minus 5, and a minus by a minus gives a plus I. So real parts together, so 4 and minus 5, that gives me minus 1, and then 3I and I, that gives me plus 4I. And now I have z2 minus z1, so I now have to get the modulus of that. So I proceed to get that the same way as I've been getting as I got the other one. So the modulus of z2 minus z1 is equal to the square root of minus 1 squared plus 4 squared. So then we get 1 plus 16, and then we get the square root of 17. And we already got that z, so I'll just write on the next page. So we got that z1, the modulus of z1 minus z2 is the square root of 17, and the modulus of z2 minus z1 is the square root of 17. So therefore the modulus of z1 minus z2 is equal to the modulus of z2 minus z1. And then we're asked, so in the next part, we're asked to give a reason why the modulus of z minus a complex number is equal to that complex number minus z will always be true for any complex numbers w and z. So basically, when we subtract, so we got that we had 1 and minus 4i for the first one, and then we got, for the next one, we got minus 1 plus 4i. But the absolute values were the same. So even though we had a plus 1 here and a minus 1 here and a minus 4 and a plus 4, so I'll just compare the two ones. So we had, for z1 minus z2, we get 1 minus 4i, and for z2 minus z1, we get minus 1 plus 4i. So those were our two values. But when we get the modulus of each of them, they're going to be the same. So the absolute values for the real and the imaginary parts are going to be the same. The absolute values because when we square a positive number, it stays positive, and if we square a negative number, it becomes positive. So they'll be the same of the real and imaginary parts, and the absolute value means the modulus parts are the same. So that means a squared plus b squared will be the same, and that's if we have a complex number a plus bi. So then the modulus of that will be a squared plus b squared. So that's a reason why it would always be the same. So then we are asked in the next part, we're asked to find a complex number z3 such that z1 is equal to z2 over z3. So because I want to find z3, I'm going to rearrange this formula to get z3 by itself. So what I'm going to do first is I'll multiply both sides by z3. So then I'll have z3 multiplied by z1, and then these will cancel. I'll get is equal to z2. And now because I want to get z3 by itself, I'm going to divide both sides by z1. So z3 is equal to z2 over z1. And I know what z2 and z1 are, so I'm going to be able to do division. So z2 is so z2 over z1, so that gives me 4 plus 3i and then 5 minus I. So now I have one complex number divided by another complex number. So the rules when I have this kind of division with complex numbers is I don't want to have a complex part on the bottom because I want my answer to be in the form a plus bi. So for that to be true, I'm going to have to get rid of the complex parts on the bottom. And one way that we can get rid of the complex parts is if we multiply a complex number by its conjugate. So say if we have z is equal to 5 minus I. We use this symbol to say the conjugate of z. So the conjugate is just when we change the sign in front of the imaginary part. So 5 plus I. But I can't just multiply the bottom by 5 plus I, or I'd completely change my fraction. But if I multiply something by the exact same thing on the top and the bottom, it's the same as just multiplying by 1. So I'm going to multiply both sides, top and bottom, by the conjugate of the bottom. So now I'll get 4 plus 3i, and then 5 plus I, and then 5 minus I, and 5 plus I. So I'm just going to bring it down here. So it'll be 4 by my second bracket, and then 3i by my second bracket. So 4 by 5 plus I, plus 3i by 5 plus I. And then 5 by my second and minus I by my second. So 5 by 5 plus I minus I by 5 plus I. So 4 by 5 gives me 20. 4 by I gives me 4i. 3i by 5 gives me 15i. And 3i by I gives me 3i squared. And then 5 by 5 gives me 25. 5 by I gives me 5i. Minus I by 5 gives me minus 5i. And minus I by I gives me minus I squared. And so I'm going to group together terms. So I have 20 and I have, so there's no other thing that doesn't have an I. So I have 4i and 15i. So I'm going to group them together and I'll get 19i plus 3i squared, and then 5i minus 5i, so that'll cancel, and I have 25 minus I squared. But I have to remember, I was told in the question, and I should know that I squared is equal to minus 1. So wherever I have an I squared, I'm going to sub in minus 1. So I have 20 plus 19i plus 3 minus 1, and then that's over 25 minus 1. So that's going to be minus 3, so 20 minus 3, so that'll be 17 plus 19i, and then that'll be over 26. So now I have to divide, because I don't want it all over something, I want them separate, so it'll be 17 over 26 plus 19 over 26 I. And that is my answer for that part.